Hey everyone, and welcome to another deep dive. Today we're going to be tackling something pretty wild. The idea that the universe might have existed before time even existed.
Yeah,
Before time as we know it. A timeless universe.
that's right.
And even wilder, it might even be able to reset back to that state.
Yeah.
So buckle up, because this is going to be a wild ride.
Yeah, it's definitely a fascinating concept. And the exciting part is that it's not just, speculation. We're talking about real science based on things like quantum cosmology, general relativity, and actual observations of the universe.
Okay, so when I first stumbled on this idea, my initial reaction was, confusion. A universe without time.
Right.
Does that even mean anything? Wouldn't it just be nothing?
Yeah.
Like an empty void?
It's a natural question to ask, but it's actually much more interesting than that. Imagine instead of nothing, a state where every single possibility exists at once, but none of them have actually happened yet. It's kind of like hitting the pause button on absolutely everything, a state of perfect balance and symmetry.
So not an empty void, but more like a cosmic pause screen?
Yeah.
Like everything's loaded and ready to go, but the play button hasn't been pressed yet.
That's a great way to put it. And this isn't just, a whimsical idea. There's an equation that backs it up, the Wheeler-DeWitt equation. It's a mind-boggling piece of quantum cosmology. But essentially it says that maybe the universe doesn't need a concept of time to exist. It's almost as if time is optional for the universe.
Okay. Started to see why you called this mind-bending.
Yeah.
But how do we go from this timeless state to the universe we see today with clocks, calendars, and deadlines? Where does time even come from?
That's where the idea of spontaneous symmetry breaking comes in. Think about a perfectly smooth lake freezing over. The water was perfectly symmetrical before, but as it freezes, it forms unique patterns of ice, breaking that symmetry.
So by freezing, the lake goes from a simple state to something more complex and structured.
Exactly. And for the universe, that, quote, freezing could have been triggered by tiny quantum fluctuations in that timeless state. It's like those fluctuations were the seeds that disrupted the perfect balance, starting a chain reaction that led to space-time, energy, and eventually what we perceive as time.
So time isn't baked into the universe, but it emerges from something deeper.
Yeah.
Wow. If that's how time began, what about the end of the universe?
Yeah.
Does this theory tell us anything about that?
This is where things get really intriguing. If time emerged from a broken symmetry, could the opposite happen?
Yeah.
Could we go back to a timeless state? That's where the concept of the Big Rip comes in a scenario where the expansion of the universe accelerates so fast that everything, even space-time itself, is ripped apart.
The Big Rip. Yeah. It sounds intense, to say the least.
It's definitely a dramatic event, but in this framework, it's not really the end. It's more like a cosmic reset, a return to that balanced, timeless state. Imagine the universe as a whiteboard, being wiped clean, ready for something new.
A cosmic reboot.
Yeah.
That's a pretty profound idea.
Yeah.
But how do we know any of this isn't just theoretical? What kind of evidence supports these mind-blowing ideas?
That's a great question. And the evidence comes from some pretty fundamental observations about the universe. Let's take the cosmic microwave background.
Okay.
The CMB for short. It's like a baby picture of the universe, the afterglow of the Big Bang.
I remember learning about that. The universe's first photo op. What does that baby picture tell us?
Well, in that picture, we see tiny variations in temperature. These variations might actually be leftovers from those quantum fluctuations that happened in the timeless state. They were stretched out by the universe's rapid expansion, becoming imprinted on the CMB.
So those temperature differences are like fingerprints from the universe before time.
Exactly.
That's incredible. But is the CMB the only clue we have?
Not at all. Scientists are searching for primordial gravitational waves. Think of them as ripples in space-time itself, which could give us even more direct evidence of the shift from timelessness to time. And these gravitational waves, they carry secrets from the very early universe, maybe even the transition from that timeless state.
So we're looking back in time to try and find clues about a time before time.
Yeah.
It feels like we're peeling back the layers of reality here.
Exactly. And this search for evidence isn't limited to looking back. The way the universe is expanding and how that expansion is accelerating could give us hints about whether it's heading for a big rip.
You mean that whole dark energy thing?
Right.
That mysterious force that's pushing everything apart?
Right. Dark energy makes up a huge part of the universe, about 70%, and some scientists suggest that it's not a thing, but a property of space-time itself. It's as if time, space, and this mysterious force driving the universe's expansion are all interconnected.
Okay, that's That's a lot to absorb. Time might not be a fundamental property of the universe. It could emerge. It could even disappear.
Yeah.
And there's real scientific evidence supporting these ideas. It's mind-blowing.
It certainly challenges our perception of reality. And what's even more fascinating is that the idea of emergent time might not just apply to the universe as a whole, but also to the quantum world, the realm of tiny particles and mind-boggling phenomena.
Okay, now we're going from the cosmic scale to the subatomic.
Yeah.
You're really taking us on a deep dive. What happens to time in the quantum world?
Think about the phenomenon of quantum decoherence. In the quantum world, particles exist in superpositions. Imagine them being in multiple states at once. But when they interact with their environment, they choose a single state, leading to the classical time-bound behavior we're familiar with.
So is it like the universe itself went through a kind of quantum decoherence,
Yeah.
going from a state of multiple possibilities to a single reality with a definite arrow of time?
That's a very insightful way to put it. It makes you wonder if our perception of time is just a way for our consciousness to grapple with a deeper, timeless reality.
Wow. That's getting pretty philosophical.
Yeah.
Sounds like we've just dipped our toes into the vast ocean of the timeless universe. What else is there to explore?
Plenty. We can delve into specific predictions about what we might observe if this theory holds, from subtle changes in time to mind-boggling quantum events.
Sounds like we're just getting started.
Yeah.
I'm ready for more. What are some of the specific predictions of this theory, and how can we test them?
That's a great question, and the exciting part is that these predictions can be tested with current and future scientific instruments. We're talking about observations that could fundamentally change our understanding of the universe and our place within it.
Okay, I'm on the edge of my seat here. Give me the predictions.
Well, let's start with the big one, the Big Rip. If the universe is headed towards a timeless reset, the Big Rip could offer some of the most dramatic and mind-bending evidence.
Hold on, back to the Big Rip.
Yeah.
But wouldn't that be, kind of a big deal?
Yeah.
Like the end of everything.
Well, remember, it's not an end in the traditional sense. It's a transition back to that timeless state. And the process itself, the way it unfolds, would offer some incredible insights into the nature of the universe. We're talking about events so extreme, so far outside our normal experience, that they would challenge our very understanding of reality.
Okay. I can see why you're excited about this.
Yeah.
But wouldn't these events be happening billions of years in the future?
Yeah.
How could we possibly observe them?
That's where things get really interesting. Remember how we talked about time being emergent and tied to energy? As space-time stretches and those energy gradients become more extreme, we might start to see localized time dilation effects,
Okay.
even within our own galaxy.
Wait, you're saying time itself could start behaving differently in different parts of the universe?
Exactly. Imagine clocks running at slightly different rates depending on their proximity to massive objects like black holes, or even just galaxy clusters. It would be like watching the fabric of time warp and stretch right in front of our eyes.
That's wild. But wouldn't it be incredibly difficult to measure those variations?
With our current technology, it would be a huge challenge. But as our instruments get more sensitive, things like next-generation atomic clocks,
Okay.
or those incredible gravitational wave detectors, we might start to pick up on these subtle discrepancies in the flow of time.
Okay. So time dilation is one prediction. What else should we be looking for?
Another fascinating possibility is that quantum fluctuations, those tiny jitters in the fabric of reality, could become more noticeable as the universe stretches towards the Big Rip.
So instead of just causing tiny effects in the subatomic world, they could start to influence things on a larger scale.
Precisely. Imagine sudden bursts of energy appearing seemingly out of nowhere, or particles popping in and out of existence at a faster rate.
Whoa, that sounds like something straight out of a science fiction movie.
It might seem that way, but it's rooted in the laws of physics. Think about the Heisenberg uncertainty principle. It tells us there's a limit to how precisely we can measure certain properties of a system. As space-time stretches and gets distorted, that uncertainty could be amplified, leading to those larger-scale quantum effects.
Okay, I'm starting to see how these predictions connect to the idea of a timeless universe and a potential Big Rip. But is there any way to observe these effects now? Or are we just waiting for the universe to, rip apart?
Well, there might be some subtle hints already present in the universe, and that's what makes this whole field so exciting.
I'm definitely hooked. What kind of hints are we talking about? Where should we be looking?
Let's start with the cosmic microwave background again, our trusty baby picture of the universe. It already contains those faint fingerprints of quantum fluctuations from the very early universe.
Right, those tiny temperature variations that we talked about earlier.
Exactly. But as our instruments become more sophisticated, we might be able to detect even subtler patterns in the CMB. That could reveal clues about the transition from a timeless state. It's like we're using the universe's earliest light to piece together the puzzle of its origins.
So by studying the CMB in more detail, we could glimpse both the beginning and potentially the ultimate fate of the universe.
It's a possibility.
Yeah.
And we're not limited to the CMB gravitational wave astronomy. The study of those ripples in space-time
Yeah.
is another rapidly evolving field that could offer some incredible insights.
Oh, yeah, those gravitational waves caused by things like black holes colliding.
Right.
What could they tell us about a timeless universe?
Remember, the Big Rip is a scenario where space-time itself is stretched to its limits. That process would create immensely powerful gravitational waves, unlike anything we've ever detected before.
So by analyzing the patterns and characteristics of those waves, we could learn more about how space-time behaves under extreme conditions.
Precisely. And those gravitational waves could carry information from the very early universe, potentially revealing clues about the transition from timelessness to time. It's like listening to the echoes of the universe's birth.
Wow. It seems like we're on the verge of a new era of cosmology, where we could use these advanced instruments to explore the deepest mysteries of the universe.
Absolutely. And it's not just about cosmology. These ideas have implications for other areas of physics, like quantum mechanics and our understanding of black holes. And speaking of black
We're
holes,
going to talk about black holes. I'm all ears. How do they fit into all of this?
black holes are fascinating objects that really push the boundaries of physics. Remember how we talked about them as regions where space-time is warped to the extreme?
Yeah, they're like cosmic vacuum cleaners, sucking up anything that gets too close.
It's more than just sucking things up. It's about warping the fabric of space-time itself. And that's where the connection to the timeless universe comes in. Some scientists believe that black holes could be remnants or echoes of that primordial state, offering a glimpse into what existed before time emerged.
Wait, so black holes could be like windows into the pre-time universe. That's mind-blowing.
It's a fascinating possibility. And by studying them in more detail, observing their behavior, their interactions with other objects, and the radiation they emit, we might gain insights into the transition from timelessness to time, and what happens when space-time is stretched to its absolute limits.
This is incredible. It feels like we're piecing together a cosmic puzzle with clues coming from every corner of the universe,
Yeah.
from the faintest whispers of the CMB to the powerful roars of black holes.
It's like the universe is speaking to us in a language we're just beginning to understand, and the more we learn, the more we realize how much we don't know, and how much there is still to discover.
This has been an incredible journey so far. We've explored the mind-bending concept of a universe that might have existed before time, transitioned to the time-bound reality we experience, and could eventually reset back to that timeless state. And we've delved into the scientific evidence supporting these ideas, from the CMB to dark energy, quantum entanglement, and even clues from black holes.
It's been quite a ride, and the most exciting part is that we're just getting started. There are so many more predictions to explore, each with the potential to revolutionize our understanding of the universe.
I'm definitely ready for more. What other mind-blowing predictions are waiting for us in this timeless universe?
Well, hold on to your hats because we're about to dive into some truly wild possibilities, including the mind-bending effects of time dilation, the unpredictable nature of quantum fluctuations, and the potential for dark energy to reveal even more secrets about the universe's ultimate fate.
This is going to be epic. So, to our amazing listeners, grab a drink, take a deep breath, and get ready to journey further into the mysteries of time and the universe. We'll be right back with more.
Welcome back to our exploration of the timeless universe. In the last part, we discussed the mind-boggling concept of a universe that might have existed before time and could return to that state. We even touched on some fascinating evidence that supports these ideas.
It was a wild ride for sure, but we left off with the promise of even more mind-blowing predictions.
Right.
I'm all ears. What other wild possibilities does this theory offer?
Well, let's dive deeper into those localized time dilation effects we mentioned earlier. Remember, we're talking about time itself behaving differently in different parts of the universe.
Yeah, it's a hard concept to grasp. But you mentioned something about clocks running at different speeds. Can you give us a concrete example of how that might play out?
Absolutely. Imagine two atomic clocks, perfectly synchronized. We place one clock in a high-gravity environment, like near a black hole, and the other stays here on Earth.
Okay, I'm picturing it. What happens next?
Because gravity warps time, the clock near the black hole would tick slightly slower than the one on Earth. It's like a cosmic time warp.
So time itself would be stretched near the black hole. Could we actually measure this difference?
With our current technology, it would be incredibly difficult. But as our instruments become more precise, we might be able to detect those tiny variations, offering more evidence for the flexibility of spacetime. And who knows, maybe one day we could even harness this effect for new technologies, like super accurate navigation or even time-based communication.
Wow, that's taking the concept of time travel to a whole new level. But you mentioned other predictions too. What about those quantum fluctuations? You said they might become more noticeable as the universe expands.
That's right. As the universe stretches towards a potential big rip, those tiny jitters in reality, those quantum fluctuations, could have a more significant impact.
So instead of just causing tiny effects in the subatomic world, they could start messing with things on a larger scale.
Exactly. Think about sudden bursts of energy appearing seemingly out of nowhere, or particles popping in and out of existence at a much faster rate than usual.
That sounds almost chaotic. It's like the universe could become less predictable.
In a way, yes. But it's important to remember that those fluctuations would still be governed by the laws of physics. It's not like things would just happen randomly.
Okay, so there's still order within the chaos.
Hmm.
But if these effects become more pronounced, wouldn't that have a huge impact on our understanding of the universe?
Absolutely. It would challenge some of our most fundamental assumptions about how the universe works. But that's the beauty of science. It's about constantly questioning, exploring, and refining our understanding.
So, time dilation, quantum fluctuations. What other wild predictions are waiting for us? What about dark energy? You hinted that it might not be constant.
That's right. Some theories suggest that dark energy might not be a fixed, unchanging force. It could be a dynamic field that evolves over time, becoming stronger or weaker.
So instead of just pushing the universe apart at a steady rate, it could accelerate or decelerate the expansion.
Exactly. And observing those changes in dark energy's behavior would be crucial for understanding the universe's ultimate fate.
Okay, so we're talking about measuring incredibly subtle effects across vast cosmic distances. How do we even begin to study these things? What tools do we have?
We've got some pretty amazing tools at our disposal. Let's start with the cosmic microwave background again, our trusty baby picture of the universe. It's a treasure trove of information.
Yeah, it seems like the CMB keeps popping up in this conversation. What else can we learn from it?
As our instruments become more sophisticated, we might be able to detect even fainter patterns within the CMB. That could reveal clues about the transition from a timeless state, or even hints of the universe's eventual reset. It's like we're using the universe's earliest light to piece together the puzzle of its origins and its destiny.
So we're not just looking back in time, we're looking for clues about the future as well. That's incredible. But you mentioned another exciting tool, gravitational wave astronomy. What can those ripples in space-time tell us?
Remember, the Big Rip is a scenario where space-time itself is stretched to the breaking point. That process would generate incredibly powerful gravitational waves, unlike anything we've ever detected before.
So by studying those waves, we could learn more about the nature of space-time and how it behaves under extreme conditions.
Exactly. It's like listening to the echoes of the universe's most dramatic events. And those gravitational waves could even carry information from the very early universe, potentially revealing clues about the transition from timelessness to time.
Wow. It feels like we're on the verge of a new era in cosmology. But with all this talk about the Big Rip, time dilation, and quantum fluctuations, it's easy to get lost in the grand scale of things.
You're right. It's important to bring it back down to earth sometimes.
Exactly. How do these mind-bending concepts connect to our everyday experience?
Well, remember those atomic clocks we talked about earlier? The ones ticking at different speeds depending on gravity. That's not just a theoretical concept. It actually affects technology we use every day. Think about GPS satellites. They rely on incredibly precise timekeeping to work properly. And those tiny variations in time, due to gravity, can impact their accuracy.
Wait, so this isn't just a theoretical concept. It has real-world implications.
Absolutely. It's a reminder that even the most abstract ideas in physics can have tangible effects on our lives. And as our understanding of time and gravity deepens, Who knows what new technologies we might be able to develop?
Okay, that's pretty cool. What about those quantum fluctuations? Can we see any evidence of those in our everyday world?
Believe it or not, those quantum fluctuations might be playing a role in one of the most enigmatic objects in the universe, black holes.
Black holes, those cosmic vacuum cleaners that suck up anything that gets too close. What could they possibly have to do with quantum fluctuations?
Remember when we talked about Stephen Hawking's groundbreaking discovery that black holes aren't completely black? They actually emit a faint radiation due to quantum effects near their event horizon. It's called Hawking radiation.
Oh yeah, I remember learning about that. But how does it relate to quantum fluctuations?
Well, some physicists believe that the very process of Hawking radiation, where particles are created at the edge of a black hole, is a manifestation of amplified quantum fluctuations.
So those tiny jitters in reality are powerful enough to create particles near a black hole.
It's a mind-blowing concept, isn't it? And it highlights the deep connection between quantum mechanics, gravity, and the nature of time. By studying Hawking radiation in more detail, we could gain incredible insights into the fundamental processes that govern the universe.
This is all so fascinating. But what about dark energy? We've talked about it potentially changing over time, but how can we actually measure those changes across vast cosmic distances?
It's a huge challenge. But scientists are working on some incredible projects to study dark energy and its influence on the universe. One project that comes to mind is the Dark Energy Spectroscopic Instrument, or DSI.
Okay, DSI. What is that? What does it do?
Think of it as a giant cosmic 3D map. DSI is mapping millions of galaxies to study the expansion history of the universe and figure out how dark energy has shaped that expansion over billions of years.
So it's like using the entire universe as a laboratory to study dark energy.
Exactly. And it's not just DSI. There are other ambitious projects in the works, all focused on understanding this mysterious force that's driving the universe's expansion.
This is all so incredibly exciting. It feels like we're right on the cusp of some major breakthroughs in our understanding of the universe. But with all this talk about cosmic forces and mind-bending physics, I'm curious about the bigger picture.
What do you mean?
Well, if time truly isn't a fundamental aspect of the universe, if it emerged from a deeper, timeless state, what does that mean for us? What does it mean for our understanding of reality itself?
That's a profound question. And there's no easy answer. It's a question that philosophers and physicists have been grappling with for centuries.
Is our experience of time just an illusion then? Or is it simply a particular way for our brains to make sense of a deeper, timeless truth? These are some pretty heavy questions.
They are. But that's the beauty of exploring these concepts. They challenge our assumptions, push us to think differently, and open up whole new avenues of inquiry. And who knows, maybe one day we'll have the answers to those big questions.
I'm ready for more. What other mind-boggling ideas and discoveries await us in this journey through the timeless universe?
Well, hold on tight, because we're about to delve even deeper. We'll explore some specific examples of observable phenomena, discuss the ongoing research that's pushing the boundaries of our knowledge, and even touch on some of the philosophical questions raised by these mind-bending concepts.
This is going to be amazing. So to our listeners, stay tuned for the final part of our deep dive into the timeless universe. We'll be back soon with more fascinating insights. Welcome back to the final part of our deep dive into the timeless universe. We've journeyed through some mind-bending concepts, we've explored some pretty tantalizing evidence, and we've even peeked into the potential future of the cosmos.
It's been quite a ride, hasn't it? And now, as we reach the end of our exploration, I think it's time to bring it all together, connect the dots, and see what it all means for us here in our little corner of the universe.
Exactly. We've talked about cosmic events billions of years in the future, but how does this grand idea of a timeless universe relate to what's happening right now?
Yeah.
To the ongoing research that's pushing the boundaries of physics.
Right.
How do we bridge that gap between the theoretical and the tangible?
That's a great question, and I think the key is to focus on those observable predictions we discussed earlier. Those are the tangible signs, the whispers from the universe that could validate this entire framework. So let's get specific. Let's dive into those predictions and see how they might manifest in the real world.
Okay, I'm ready for specifics. Remind me, where should we be looking for these signs?
Well, one of the most fascinating areas to watch is the behavior of black holes. Remember, we talked about them as potential remnants of the universe's timeless state, offering a glimpse into what existed before time emerged.
Yeah, those cosmic enigmas that warp time and space to the extreme. How can we use them to test the idea of a timeless universe?
By studying them closely, we might be able to find evidence of those amplified quantum fluctuations we discussed earlier. Remember, some physicists believe that Hawking radiation, the faint radiation emitted by black holes, is actually a result of those fluctuations.
So those tiny jitters, in reality, are powerful enough to create particles near a black hole. It's like the universe is showing us its quantum hand.
Exactly. And by studying those particles, by analyzing the characteristics of Hawking radiation, we could gain incredible insights into the interplay between quantum mechanics, gravity, and the nature of time itself.
Okay, so black holes are definitely a hot spot for finding clues.
Hmm.
What about those localized time dilation effects?
Right.
We talked about clocks ticking at different speeds depending on gravity. Is that something we could actually observe?
It's a tough measurement to make, but as our instruments become more precise, it might be possible. Imagine two atomic clocks, perfectly synchronized, but one is placed in a high-gravity environment, say near a massive galaxy cluster,
Okay.
while the other stays here on Earth.
I'm picturing it. And because gravity warps time, the clock near the galaxy cluster would tick slightly slower.
Yeah.
Like a cosmic slow motion effect.
Exactly. And while this effect is incredibly subtle, it could be detectable with next-generation atomic clocks. It would be like watching the fabric of time warp and stretch right in front of our eyes.
Okay, I'm starting to see how these predictions can be tested, how they bridge the gap between the theoretical and the observable.
Yeah.
But what about dark energy? You
Right.
talked about it potentially changing over time, becoming stronger or weaker. How can we observe those changes across vast cosmic distances?
That's where things get really challenging. Dark energy is elusive, but we can see its fingerprints on the large-scale structure of the universe.
You mean how galaxies are distributed and how fast the universe is expanding?
Exactly. By studying those things, by creating detailed maps of a universe and measuring its expansion rate with incredible precision, we can try to figure out if dark energy is constant or if its influence is changing over time.
So we're using the entire universe as a giant laboratory to study dark energy and its potential connection to the timeless state.
Yeah.
It's like a cosmic detective story.
It is, and there are some amazing projects underway that are pushing the boundaries of observational cosmology. We already talked about the Dark Energy Spectroscopic Instrument, or DSI, which is creating a 3D map of millions of galaxies. Yeah.
But there are other ambitious projects in the works, like the Large Synoptic Survey Telescope,
Oh, wow.
which will capture images of the entire southern sky every few nights, allowing us to track the movements and changes of billions of celestial objects.
Wow. It's incredible to think about all the data that's being collected and analyzed, all these different approaches to unlocking the universe's secrets. Feels like we're on the cusp of some major discoveries.
Absolutely, and I think those discoveries won't just be about the universe out there. They'll also have profound implications for our understanding of ourselves,
Okay.
our place in the cosmos,
Yeah.
and the nature of reality itself.
You're right. It's like this whole journey through the timeless universe has brought us back to those big questions we were pondering earlier. What is time?
Yeah.
Is our experience of it real or just an illusion? Those are questions that have puzzled philosophers and scientists for centuries, and I don't think we have all the answers yet. But the beauty of science is that it's a process of continuous exploration, of asking questions, seeking evidence, and refining our understanding.
And even if we never find all the answers, the journey itself is incredible, isn't it?
It is.
It's about pushing the boundaries of human knowledge, exploring the unknown, and embracing the mystery of it all.
Couldn't said it better myself. This whole deep dive into the timeless universe has been a perfect example of that. We started with a mind-bending concept, explored fascinating evidence, and ended up with even more questions than we had before.
It's been an amazing adventure. And to our incredible listeners who joined us on this journey, thank you for diving deep with us. Remember, the universe is full of wonders waiting to be discovered. And the search for knowledge is a journey that never truly ends.
Keep exploring, keep questioning, and keep your minds open to the infinite possibilities of the cosmos. And if you're hungry for more, be sure to check out the show notes for links to all the research we discussed and resources for further exploration.
Until next time, keep looking up and keep diving deep into the mysteries of the universe.